Okay, guys, so today we will discuss the in-depth concept of action potential. We have this basic introduction to action potential in our colleges, right? But let me tell you what exactly action potential work and why it is actually present in the body. So let's just start off with the basic concept. For example, you have two chambers, right? And what happen? Each of them have electrons in it. For example, this one has 50 electrons. This one say have 50 electrons. What happen when you connect both of the channels? What will happen? And you just you connected these channels and you put a voltmeter in between them. How will it respond? Will it respond? No. Why? Because the potential is different on the both of the same side. So electron won't move. But for example, let's just change it a little bit. For example, now you have your another chamber part B, which is say connected to a voltmeter, right? And in this chamber you have, for example, 6 electrons. Okay, and in this side you have 10 electrons. Okay, so this side you have 6 electrons, this side you have 10 electrons. So now what happened? From this side, electron will move on to B chamber, right? From B to A. Why? Because always everything in a universe tend to go to a low potential surface. Why? Because we choose to have a low energy phase, right? So that's why this we have seesaw and this will shift. So it will show a shift in potential. So current will flow. This will act as a negative charge and this will act as a positive charge. Positive charge is nothing but a absence of electrons, right? You know how in semiconductor we have learned when electrons move from their location, then they leave a charge. Look, when they move from one position to another position, they leave empty space, which is known as holes, and this hole act as a positive charge. So in this way, we can just assume that if a charge is moving from one chamber to B chamber, only in the presence of potential difference, in this situation it is electrical potential difference, this will induce current, or you can say charge, right? So that's what happened. Let's just discuss what happened in our cell. So you have a cell membrane, right? And what are the bands around it? It's a charge outside of it. What are the charges like sodium, chlorine, potassium? Same, it has charge inside. Sodium, chlorine, potassium, calcium, right? How calcium is very important in muscle action and fighting reactions. Calcium is much needed in all of their procedures. These are very important cation which we cannot avoid. Also, what else we have here? Amino acids in proteins, right? They could be negative charge or they could be positive charge. So we have a imbalance around the cell membrane. This is ECF and this is ICF. So, for example, what happened in case of a cell is we have multiple channels around our cells, right? Multiple channels. For example, we have potassium channels, which are open channel, in which potassium is freely movable. It can move between in and out. We have calcium channels, right? And we have sodium channels, which are either ligand gated. Ligand gated means they need a ligand, then only they can open. It's like a gatekeeper. Voltage gated. After voltage decrease to certain point, the channel will open. But only these potassium channels, these are freely movable. They can move in and out. They are like Vijayamalla. There is nothing that can stop them. So what happen is How do we manage the balance then? We have a special enzyme here, sodium, potassium, ATPase. This is the most important item because if we do not maintain the balance, what happens? There is increased amount of potassium charge in there. So in whichever side we have more solute, water will travel, osmosis will occur, right? When osmosis occur, hyposolution, hyper, water will move from the hypo to hyper. And if we have more salt here, more cation here, then water will move inside, and what happens? The cell will swell up and it will burst. That's why we need to maintain a balance between cations. But how does this sodium potassium ATPase maintain the balance? When we look in at depth in this uh, channel, what we see is this one have a very special constitution. This is how it look like. This is how a sodium potassium ATPase look like. What's so special about it? What does it do? It have three active sites inside of the cell and two sites outside of the cell. Right? So what happens is, for example, it just attract three sodium channels. It can control this, it can attach to three sodium channels. And on the outside it will attach to, that is written in different color, it will attach say two potassium. Okay, so three sodiums and two potassium. Now what happened? There is a ATP attached to it. What happened with this ATP? What happened with this ATP? When this ATP break, what will break into? ADP plus me P, inorganic phosphate, and what happened? It will release a huge amount of energy plus a huge amount of energy. And what will this energy do? It will change this enzyme. What will happen to enzyme? It will revolve around. It will change its shape. From this, it will become like this. Now what happened? Our sodium gets outside and our potassium get inside. Right? So what happened? We just throw out. What does it do? We just throw out sodium outside of the cell and potassium inside of the cell. So how do we remember it? Nokia, three sodium outside of the cell, two potassium inside of the cell. 3 to 1 Nokia. Right. So now we look at overall picture. Right. So what just happened? We have balance in between all of them. But what does this any sodium potassium pump do? It will throw three sodium outside and two potassium inside. But there's a difference. There's exchange between ECF and ICF. But we have overall one positive charge outside. So what will happen? Now we accidentally, or we can say intentionally, created a positive charge outside of the cell, and we have negative charge. Technically, when I say it's a negative charge, doesn't mean there's an electron inside it. Or when we say there's positive charge outside, doesn't mean it's just all protons or all positive charges outside. No, it could be a balance between. There will be sodium present, there will be potassium present, there will be chlorine present, there will be proteins present. Okay. Same here. Sodium, potassium, chlorine, calcium, they all are present. But when we say net charge is outside as a positive charge, and negative charge is as a net charge is inside. Okay, so don't take it as a likewise the only positive charge are outside. When you see a question, what is the chlorine concentration outside of the cell, or what is the potassium concentration inside of the cell? You won't miss it out as no, there is no sodium inside, or there is no potassium outside, or can be likewise anything. Okay, so you just have to remember more positive charge outside, less negative charge inside, due to more sodium outside and less potassium inside. And who created this potential? Are sodium potassium ATPs. So this charge at at normal state. Okay, this charge is known as resting membrane potential. This is potential difference of a membrane in a resting stage. When what do we mean by resting stage? Resting stage means when it is in normal state, when there is no active function is going on in the cell. Okay. So what are the values here? RMP for neuron is very common, minus 70 millivolt. Minus 70 is necessary because inside it is negative. In skeletal muscle, it is minus 90 millivolt. Same in ventricle. That's why I want to discuss this. Because when I'll be discussing the ECG and all cardiac cycle, it is going to be a very important part. Okay, minus 90 millivolt. On SCA node, even though it's a part of our heart, and even though it's supposed to be a very similar charge, but not, it is minus 55. And for smooth muscle, okay, it's vary from minus 40 millivolt to minus 60 millivolt. It is somewhat in between this neuron and smooth muscle. So each kind of muscle have different kind of resting membrane potential. When they ask you, like for example, they used to ask you, which of the ion is responsible for RMP? For the RMP, or for example, is a neuron. Which is the responsible ion? Who maintain this as? Like we can have sodium, they say potassium, or they say calcium, or they say chlorine. Who is more responsible? You can say like the very first question will come into mind is sodium. But yes, it is the sodium which maintain a plus one difference outside of the cell, but it is not the reason why it is stationary there. Like for example, it just can't move out on its own, right? Like if somebody asks you who is the cause of the corruption, you can't say someone who is restricted only. He can't do it things on his own. Who can move freely outside of the cell, inside of the cell? Potassium. He is the main culprit. He can move in and out. It can change that potential difference. It can vary the potential difference, right? If they ask you equilibrium potential, like you just say ki, your RMP of your neuron is in equal to equilibrium potential of which ion? It's chlorine. They are one of the two most complicated and most asked questions. Who is the responsible for RMP? Potassium. Which enzyme? Sodium, potassium, ATPase. Who is RMP of a neuron is equal to potential of what? Which ion? Chlorine ion. You can say chlorine have a potential of around minus 70 millivolt. Right? So now we have understood this concept. Let's just say now we want to understand what is action potential, how actually it works. So let's just draw a little graph here. This is your cell wall, okay? It's positive here, it's negative here. We have small sodium channels on our wall. These sodium channels can be ligand gated. What does ligand gating mean? It means that if a certain cation or anion, something like if they say that calcium gated sodium ions, calcium gated sodium channels. What does this mean? That this channel will only open if calcium attached to it, otherwise it won't open. Voltage gated, what does it mean? They will only open when there is a certain decrease in voltage, right? So now that we understood the concept, like we know all of this. So for example, what I did, I just placed a, say, a voltmeter here. But you can see the electrons are going from here, positive charge is going from here to here, then it is slightly negative, right? And let's just draw the graph here. Okay. So say it's a line, and then this is a line, and let's just draw this is 70 minus 70 minus 60 minus 50 minus 30 minus 20, and this goes to 0, and then it then goes to 10 plus 10, actually 20 plus 30, right? So what is the action potential right now at this stage? Action membrane potential is 70, right? So what happened when, yes, say there is a charge coming, and then the charge, there is any stimulus, for example, now stimulus or any kind of stimulus which is stimulated, and what happened because of the stimulation, we will discuss that in, and when we'll discuss the neuromuscular junction, don't worry about that, okay? So when there is a stimulus, this sodium channel will open. So sodium channel are opening. So what happens when there is a sodium influx? There will be a sodium influx. Sodium influx. So what do we have? Normal RMP, right? We have a normal RMP. Then what happened? We had a little stimulus. What does the stimulus do? Open the sodium channel. Now things change. What happens? Sodium channel. Positive charge, which is actually a sodium influx. Influx means moving inside the cell. In cell. So what happens? There is more positive charge inside of the cell. Okay. So now what will happen? The charge which was minus 70 millivolt, it will go towards positive, towards 0 or positive, right? Because it's becoming less negative. Become less negative. So now what happens? This charge become minus 70 to minus 60, minus 60 to minus 50, right? So when we say, like, when we start up, there is, say, one channel open, right? One channel open, it will stimulate, like, these channels are voltage gated, like, for example, these are voltage gated. So lower the voltage, higher they will open, like for example, at minus, for let's say minus 60, two channel will open. But at minus 15, more will open, right? At minus 40, more will open. So in this way, we can say it is, a chain reaction. How there is chaos happen in a crowd. Like in a crowd, one person cry or one person fell, or one person started running towards, like somebody shot a bullet. One person started to run, and just when the one person started to run, and somebody else will see him, and he will start running too. And after that, more will start running, and this way, everyone start running. You just create a chaos. It's just chain reaction. One started everything. It's just like, in Diwali we have that crackers, a long chain of crackers, and you can just fire one, and then one cracker will initiate the another one, and another initiate the another one. Right? It's the same sequence. So it's just chain reaction. One will open more, and more will open way more. So at this point, say around 55 or something, you know now enough amount of, like, it just like every channel become chaotic, all of them start opening once and around. Same as crowd. Two people running, it's okay. 10 people running, it's okay. Like out of 1,000 people, for say 200 people are running, then everyone start running. Everyone go chaotic. Two people, nobody will notice. Five people, nobody will notice out of 1,000. 10 people, nobody will notice. But if 200, 300 people are running, everyone will notice. Everyone will go into chaos. That's what happened here. That's when every sodium channel start firing. At this point, which is shooting point. This where shoot the potential will shoot. This will go to zero and then it went to more positive. Up to this point, you can see channels are opening like it's just chaos, it's just firing at hell, repeated firing. But what happened when we are, at this point? At this point, why not going up to, like, say they're going to plus 30? Why not plus 40, plus 50, plus 100, 200? They can't go back because those channels which are open here start closing here, isn't it? It's just like a chain sequence, right? Even though number of channel are opening increasing, but number of channel which are closing also increasing, right? So those who started early will start closing. Also, there is potassium which will start going inside because there is always electrical balance in between us, right? Two will move, then it is like seesaw, right? If two people here, one people here, one person come here, then one person will go around here. They just want to maintain the balance. So the moment sodium go sodium go inside, potassium will start going outside because they're open channels. Potassium are open channel, they can move outside. So the moment sodium going inside, potassium start going outside. But sodium channel are weak, you can say they fire at very high, like then suddenly they'll get silenced too. So at this phase, maximum sodium channels are open, right? This is where it started. This is the maximum number. And then what happened? Start closing. Sodium channels start closing. And at this phase, what happened? It will start to decline. And why they are declining? They are declining due to potassium because if charge is coming inside, then more charge is going to outside. And when more charge is going outside, it will become more negative. That's what happened. That's what sodium do, right? There's sodium. How do sodium maintain the potential? By making the more amount of positive charge outside. So that's what potassium doing now. It's maintaining a more positive charge outside. At this phase, all sodium channels are closed. Sodium closed. Only potassium open. But potassium open channel, they are slow. These are fast closing and these are slow closing. Potassium channel are slow. So what happen? They overdo the things. They overdo. They just make it more negative one. Right? Just as Himalaya, like Vijay, they'll make you more poor. If you're going to, you just take the charge of making it negative, they'll make it more negative. Right? So they're free to go. They will do more of the job, more than required. So that's why they will make it more negative than the resting membrane potential. And then when it will start to come back to normal. And who do that job? Sodium, potassium, ATPase, which will bring it back to resting membrane potential. So without RMP, it is not going to come back. So let's just discuss it again. What exactly happening here, right? Let's just get a clear idea. Again, we will discuss it, right? It's just minus 70 here, 60, then says 0 here, then plus 10, then plus 30. RMP, normal resting membrane potential. Some sodium started influx, shooting up. There's a lot of firing, a lot of sodium channel open, maximum open, can't go anymore. Potassium opens, now going downside. Potassium's doing over job, lead to hyperpolarization. Then that's what happened. You know, there is RMP, sodium channel started opening, chain reaction. Okay, so that's where firing occurred. That's right. Maximum sodium channel open. Sodium closing potassium opening. So here what is happening? You can say here sodium influx. Here potassium efflux. No, you can say here where sodium channel are going into chaos, and here where potassium as a police stabilizing the chaos. Okay, and this point, what happened? This phase is this part. This is hyperpolarization, right? At this part there is hyperpolarization. More potassium efflux. Okay. So what do we call this phase? This part is known as depolarization. Why? Why it is depolarization? Because here our resting membrane potential is polarized. When it's reaching to zero, we are calling it depolarizing because its polarization is removing. When it's something going towards the zero, it's depolarization. The same way deforestation work when there is a lot of forest in there, more of the tree. So when you try to cut the tree, when you try to make it zero, we call it deforestation. So when there is polarization, means there is a charge on your membrane, but you are trying to make it zero. That is known as depolarization. What do we call this phase? This is depolarization, and this phase is depolarization, right? We are trying to depolarize. We are making it from zero to minus 70. Yes, it is go up to positive, but that's not a concern, right? No, it's just trying to go back to zero, right? So that's why depolarization. It's going more negative now. So it's depolarization. What happened here? What do you call this phase? This is hyper depolarization. Mean we have overdone the work. We don't want it to be this much polarized. We just want it to stop at minus 70 and not go up beyond that. So that's why it's hyperpolarization. And it is the job of sodium potassium ATPase. You know, now we have sodium inside of the cell, so these will kick out the sodium out of the cell. They're doing this work continuously. But this hyperpolarization state will be stabilized by the sodium potassium ATPase. Okay, so this another thing I want you guys to know. You know, at this phase we cannot induce. Let's just say we'll just highlight this phase. Okay, this phase up to here. We this phase is a stage where sodium influx is going on. Sodium channels are open. Can we open more sodium channels? What I'm saying is, for example, there is a chaos already going on. Can I create a more chaos? No, I can't do anything about it. Even there's a chaos going on because of a bullet fire. Can if I shoot more bullets, will there be a more chaos when it's already at its maximum point? No, nothing more will happen. So, for example, at this point, if you give any stimulus, there is a stimulus, right? And there is action potential, but at this phase, if you give another stimulus, there won't be another action potential. At this phase, you can't have another action potential. But at this phase, but at this phase, sodium channels are closed. So those channels can be reopened. Like at this phase, a small amount of people settle down. So you can scare them away again. That's what you mean by this is uh, this is a absolute refractory. Absolute refractory phase. And this is a relative, right? This is resistant but very less. This phase is super resistant to any any stimulus. You can't create another stimulus in this phase. So this is what I actually mean. For example, this is your muscle and you are giving a stimulus and stimulus occurs. If you give another stimulus here, say another stimulus, so will it go like this? No, it will stabilize. It won't. You will do nothing to the stimulus. It will just go as it normal path. That's what happened, right? That's how stimulus go. But what happen when you give stimulus at this phase? What will happen? At this phase, if you give, then what will happen? Nothing. It will go as usual. But you don't want to make that change, right? So what you do? You if you give stimulus at this phase, what will happen? Then this will happen. It is delta refractive phase, but you are given stimulus strong enough. Has to be strong enough. You can't give it below the threshold. If you given it below stimulus, you can induce another stimulus. If you give it here only another stimulus, it will go for hyperpolarization. Then it will go for hyperpolarization. You could create this phase. Okay, you could create this phase of hyperstimulation, but only if you give the stimulus at the relative refractive period, and it has to be a strong one. You can't create it with a lower one. Okay, so this is our action. So we have understood that what does sodium do? It will induce the action potential. What does potassium do? It will stabilize the action potential. Okay, so you can say, like, now we have a doubt. Okay, now we have a question, right? So for example, if we increase the amount of sodium atoms around, like, we have hypernatremia, right? Mean there is a more amount of sodium channel outside of the cell. So this is our how a normal action potential will look like, right? It will look like firing, hyperpolarization, like this. So what happened? We have increased amount of sodium channel. Then what will it do? It will increase the amplitude. This it will do. In case of hypernatremia, why? Because more sodium mean more sodium to excite. More sodium influx will occur. Like, more sodium in more sodium influx lead to more depolarization. It just seems like how if increase like if you increase the number of the people, then chaos will increase. There will be increased amount of chaos, right? So if they are less sodium, say they are less sodium, then what will happen? This will happen. More sodium, hyponatremia, right? Less sodium. What happen when you have more potassium? Then what does potassium do? What does potassium do? This is a normal, right? 60. If you have less, then it will become 80. Less potassium become 80, right? So you just think it as potassium is directly proportional to excitability, and a sodium is directly proportional to amplitude. Okay, so more sodium lead to early or easy excitation. More increase amplitude mean high action potential. What that mean? You need less stimulus. Okay, so these are the basic introduction to a action potential. We will summarize, we will learn more about it when we will discuss the neurophysiology part. But for now, this much was needed to understand the concept of cardiac cycle and ECG specifically, which will be discussed.